Welcome to the Corticare webinar series presented on the Asset Central platform. We're presenting topics related to EEG in neurodiagnostics, patient care management, research, and future applications. With recent release of ChatGPT, the role and the impact of artificial intelligence technologies has become a hot topic. Healthcare has seen tremendous investment in AI technologies over the last decade, and it is expected that the AI tools will play a significant role in neurodiagnostics and the future of patient management. Today's webinar will present a look at the state of AI in the neuro-intensive care environment and the role EEG technologists have in its implementation and use. Presenting on this topic is Dr. Alan Waziri. Dr. Waziri is a neurosurgeon and a translational neuroscientist. His initial training was completed at the University of Iowa, and he completed his clinical and research training at Columbia University and the National Institutes of Health. Previously, he was the director of the Brain Monitoring Lab at the University of Colorado, the director of Neuro-Oncology Program at Inova Neuroscience Institute in Virginia. And more recently, he is one of the co-founders of ICE Neurosystems, a neuromonitoring platform designed to provide early warning and to guide treatment for patients with brain injury in the ICU. The company's platform integrates novel devices, next-generation software, and big data approaches to diagnose and prevent brain injury in critically ill patients. He's particularly qualified then to present today's topic of the future of neurodiagnostics in the age of ChatGPT. Welcome, Dr. Waziri, and it's all yours.
Thanks, Jeff. I'm just going to go ahead and kind of share my screen here. It's nice to meet everybody, and obviously, my background is not in machine learning or artificial intelligence per se, but I've got obviously quite a bit of experience in the clinical side, and really what we've been focusing on for many, many years now is data, and particularly the applications of EEG data, multiparametric kind of systemic data, particularly in the care of ICU, critically ill patients. But obviously where all of this goes over the long term is towards leveraging that data for better clinical application. I think there's a lot of conversation now about AI, and justifiably, because what's happening now is going to be transformative for humanity, not just for medicine or other scientific applications. And I think that there are a lot of realities, but there's a lot of myths. And so kind of during this talk, I'd like to maybe just bring up some of the basic high-level concepts that I see, as related to translational aspects of AI, some of the relevant factors that are associated with using AI with EEG, and then eventually, where does this go in the future and the role of EEG technologists in this process. So as Jeff mentioned, I am the CEO and co-founder of ICE Neurosystems. I'm going to show you some data from our platform, but not really relevant to what we're talking about today. AI is coming. So I think that clearly this is something that everybody needs to be paying attention to, how quickly it's going to impact our lives and in what areas it's going to impact our lives. That really is a topic of deep discussion, not just on a practical level, but potentially a metaphysical basis. But clearly it's going to be coming to selected applications. And I think that that's one of the things that we really need to focus on, is that AI will solve some problems very quickly. The role of AI in some problems is going to be very far off in the distance, and I'll talk about that a little bit. So ChatGPT. So this was something that was done by one of my intrepid team members when ChatGPT kind of first came out. And the question that was placed was, explain in a flowchart format how to use EEG to predict patient outcomes. And within about 40 milliseconds, this is what ChatGPT came up with. So this is eye-opening from the standpoint of the AI being able to very quickly come up with a strategy based on its ability to analyze the crazy amount of data that's present in the web, in terms of creating a plan. However, actually functionalizing these things, they all have kind of deliverables that are associated with them, But that first point, gather patient data, that has to exist somewhere for a machine learning algorithm or an AI to be able to generate the rest of this process. So all of these various components are still going to require some amount of input that has to be available to the system. Really quickly, some very high-level definitions. As you can tell, I'm using pretty simplistic sources for these definitions, but I think that they're a good overview of what we're talking about. So ultimately, AI, functionally, what we're trying to create are computer systems that normally are performed that can perform tasks that are normally provided by humans. And that's kind of a complicated variable. If it's simple stuff like helping you answer questions in your accounting table or something like that, I think AI can do that very quickly. However, as you'll see later, there are much, much more complicated things that are performed by humans that AI is not really anywhere close to performing. Machine learning is just the process by which AI is generated. So systems that are built to basically bring in data, process data, and then create some sort of an output. And the key thing there is that it doesn't necessarily have to follow explicit instructions, meaning that you can give it some kind of a higher level kind of requests, and something will come out in the background. Heuristics is something where we use a lot of shortcuts, and we may not even realize those things. They're not at the level of our consciousness, but we come up with conclusions that are driven by prior experience, a certain amount of data collection, the environment within which we're making that kind of decision. And oftentimes we can't necessarily explain what we're doing. And there's similar variables that are inside artificial intelligence generated by machine learning. And then there's a difference between explicit knowledge, which is something that we can repeat. So for example, if somebody tells you, explain to me how you get from your house to work, you can walk your way through that and say, we turn right, turn left, so on and so forth. But then implicit knowledge is something that is a little bit more variable. You may not recognize it. For example, if somebody is playing you a pattern, there's a series of notes that you're hearing, and it's repeated over and over again. If somebody doesn't tell you up front that there is a pattern, your brain over time will start to recognize on an unconscious level that there is a pattern, but you may not be able to repeat it. At some point when you recognize that there is a pattern and then you can repeat it, that's when the transition to explicit knowledge comes in. And I think that's one of the variables here that's going to be really important for EEG. If you talk to a neurophysiologist and say, take a look at this EEG pattern, what do you think this is? A lot of it is subjective. It's prior experience, it's gut instinct, so on and so forth. They can't tell you exactly what it is that's telling them, that drives them to their conclusion. And there may be some amount of implicit knowledge inside that versus an obvious pattern that you can explicitly describe why that's different. Some of the theoretical benefits of AI, these are the things that we all talk about and are also concerned about. Accuracy, clearly. If we've got something where a computer is driving your car, at some point we would assume that the computer is actually going to be able to do that in a safer fashion than in a human. Speed, improved workflow, quite clearly computers can process information at a level and scale that human brains simply will never be able to do. There's also a really important variable here, which is the creation of otherwise unattainable outputs. We may not be able to process multi-parametric data in a similar fashion to a computer-based system. And so there are potentially things that we can pull out of data that humans simply can't without a significant amount of effort. Ultimately, the question of cost and reliability, these are the things that are the human factors that are going to have to be factored in ultimately for this competition between human and machine over time. So in terms of the role of AI in medicine, the essential role of any diagnostic technology, and this is clearly going to be essential for artificial intelligence as well, is that there needs to be a provision of information from the diagnostic technology that leads to an action. That action can be a clinical intervention. Does it tell you to go get a CT scan? Does it tell you to start a medication? Does it tell you to do an operation? Or it can be counseling. It can give somebody some information about the likelihood of some other outcome based on a diagnostic test result, or ultimately prognostication. If we're trying to figure out what's going to happen to a patient based on some diagnostic information, there always has to be an action or some sort of an outcome coming from the information. That can be simple. So for example, if we're doing genetic testing for cystic fibrosis, If you have the genetic mutation, then we know that you have cystic fibrosis. That's very simple. Next level up would be something like imaging like a head CT, where the head CT may be performed, the AI may tell us that there is a metastatic tumor in the brain, but then the decision about what to do about that may not be totally clear. Ultimately, when we get to the level of EEG or continuous EEG, that's far more complicated because there's multidimensionality to the data flowing through the EEG system. And in many cases, we don't know for sure what we're supposed to be doing with that information. If we don't have information that leads to or supports clinical action, it becomes kind of a question of what's the point. The clinical action could be standardized, meaning that there's kind of a one-to-one correlation between the data point and the clinical intervention, or it could be more subjective. So in the case of EEG, if you've got a patient that's got epileptiform activity, there could be some subjective overlay as to whether or not we start an anti-seizure medication or take some other clinical action or just observe that patient. And that's really important, as you'll see later, in terms of determining whether or not AI is going to be able to serve a role in that situation. One key thing is how fast does the clinical action need to be provided? So in the case of an outpatient EEG, where you may have a couple of days and it's largely used for diagnostic or monitoring purposes, it could be okay to have data coming back in 2 days. However, if you're taking care of a patient in the operating room who's having a carotid endarterectomy, you may need to be able to respond in seconds to avoid a stroke. And so there's a key element there of how fast we can get the information and act upon it. And ultimately, who uses the information and provides the clinical action is really critical. Is it a bedside nurse? Is it another physician? Is it a caregiver somewhere else? Is it a family member? Those kinds of things are very important. And ultimately, is it the human or is it the machine that's providing the action? So in the human case, information would come in. There would be an intermediary, the human of some sort, that maybe interprets that data, but then ultimately provides the action, whether it's giving a medication, whether it's taking the patient for a scan, so on and so forth. Eventually, there are going to be certain applications where the AI itself can drive the action. For example, with sedating medications, if a patient is receiving sedation for mechanical ventilation or anesthesia or something like that, based on the data flowing through the system, ultimately the AI may be able to control the IV pump far off in the future. There's obviously a lot of steps that have to occur in there, but theoretically, it's very likely that that's going to happen. And ultimately, this can be very different for every clinical use case. So taking a monolithic view of AI in medicine, I think, is going to be difficult because there's going to be a lot of different versions of that. On a really simple level, and my CTO will probably laugh at me later for simplifying it this much, but on a very basic level, there's a couple of different components that go into creating an AI platform. At the core is the machine learning, which kind of leads to the AI. And I think the ChatGPT side of this and all of the other generative AIs that are coming out now are kind of pointing out that this is getting easier and it's getting faster. Machine learning techniques are advancing very, very rapidly. And the tools to leverage those techniques are getting simpler. I mean, ultimately, the AIs are going to be able to make easier and easier platforms through which we interact with those machine learning systems. And so there's going to be this kind of acceleration, I believe, in this whole process. One huge variable here, and this is the difference between human and machine to some extent, is that the human brain, as complicated as it is still a finite object. And there's a certain amount of defined processor and storage power within that organ. And we simply can't expand upon that. All of the Neuralink ideas and brain-machine interface about somehow expanding our minds, that's really far off, if ever, in the future. But what we can see on the AI side is that we can basically build essentially unlimited processor power, storage in cloud applications. And I think that's what's very interesting about the fact that Microsoft, Amazon, these entities that have these huge cloud architectures are focusing so much on AI, is that the capabilities of AI, I believe, are rapidly going to outstrip the human brain. And ultimately, the inputs into these machine learning AI type of situations are becoming more and more agnostic to data input. And I think that's a really important variable to consider. But ultimately, you've got the machine learning at the core, but there has to be some question that you're trying to answer. So that really kind of is the output or the action that we're looking for in terms of that AI to function. The possible outputs are information that leads to a clinical action, which is kind of a passive role, meaning that the AI takes in data and provides information to a provider who then decides to make a decision based on the information that's provided. One step up from that is information from the AI that would recommend a clinical action. So for example, if you're a bedside nurse, there's data coming through the system, the AI analyzes that data and says, this looks like the patient is having a stroke, or this looks like a patient that is over sedated. We recommend decreasing the sedation level. That's a much more complicated variable, but in that case, you have the machine directing the action of the caregiver rather than the machine just providing information to the caregiver. And ultimately, down the road, there will be AIs that perform direct clinical action, whether it's controlling the IV pump or, in much more complicated scenarios, potentially doing a surgery, doing a procedure, so on and so forth. But this is the most critical thing from my perspective in order to be able to functionalize any of these AIs, is that you have to have data. And the data matters on many, many levels in terms of not just being able to address specific questions or problems, but even being able to build an AI that can answer those problems. So uniformity of data is fairly key. We've got so many different fragmented types of data out there right now, and putting those in a format that can be put into a system in common fashion has been a big challenge for a long time. You have to have high quality data. If you've got bad quality data going in, you're very likely to get a bad outcome, or a bad output from the machine learning aspect. And so focusing on data quality is going to be a really important thing going forward. Annotated data is key, because if we can't basically say that these are the cases that we're looking for. So for example, in supervised machine learning, we can basically parse out and say, this is condition A, this is condition B, find the difference between the two, versus unsupervised learning, where you would have to have massive, massive amounts of data and say, go looking for the problem. Integrated data, particularly in our field, is going to be much more important. If you just have brain data in isolation, but you do not have other systemic physiological data, heart rate, blood pressure, so on and so forth, the brain is an organ like everything else. If the changes in the brain that we see are actually related to low blood pressure, we need to have both of those data sets together in order to be able to draw the effective conclusions. Ultimately, we have to have large amounts of data in order to be able to answer the questions that we're looking at, because of variability in human physiology and clinical scenario and so on and so forth. But ultimately, you need to have output relevant data. So if you're looking for seizures and you want to create an AI that diagnoses seizures, you have to have some data that has seizures in it. And if you don't have that, you can't answer that question. So I think correlating the output or action function of the AI is going to be heavily dependent on output relevant data that's going into the machine learning algorithm. And then one other real world practical variable that we have to consider is that it's not just the process of making it. There are other considerations to think about. First of all, there has to be somebody that will accept the use of the AI in a clinical scenario. So whether it's hospital administration, hospital IT, do we worry about cybersecurity? Do we worry about HIPAA compliance? So particularly in the medical space, it's going to be much, much longer and more complicated for us to get these into clinical deployment, because we have these other real world variables. And potentially most importantly, in order for us to be able to effectively leverage these in the medical world, somebody has to approve it, meaning the FDA, the regulatory bodies have to say, yes, this AI is accepted for use in the clinical scenario, which is going to be a big challenge in many cases. And ultimately, as we all know, somebody has to pay for it. And so those are going to be some other rate limiting steps that we have to deal with. And then really kind of on a simple basis, there's going to be some generations of medical AI that we're going to go through. This first generation, which is basically 2D data, are things where there's just a static single point in time, agnostic to other patient variables, types of data sets, radiology, pathology. These are already very advanced. These things have gone through the FDA and are actually starting to be used in the clinical setting. The next generation will be more 3D data for things where you have a particular diagnosis at a particular moment in time, and you have to layer in some other variables, patient allergies, previous medications, so on and so forth. And this is ultimately where IBM Watson was trying to go. And this is where, kind of that microbiology, oncology, and potentially seizure diagnostics field may go in the future. But one key thing about these first two generations is that these are really moment in time. There's a patient, there's a data set, there's an interpretation of that data at that moment, and then we move forward from the clinical perspective. Gen 3 is where I think we need to see a lot more work, and that's really what we're focused on, is that you have somewhat more 4D data, meaning that at any moment in time you have a package of data, but then that data evolves on a moment-to-moment basis. And this is where you maybe move from an AI that exists from previous training into an AI that learns something about that patient as it's continuing to monitor it. And then the final generation is going to be robots, driven by machines that replace the physical activities of humans. And this is going to be much, much more complicated. From the surgeon's perspective, there are things that I know we need to pay attention to, but when I'm in an operation, there are subtle things that I may not even recognize that you can't. This goes back to the explicit, implicit knowledge thing, where it's going to be much more complicated. There are a lot of clinical applications of EEG, as we know. Seizure diagnostics is a very small part of all of the various applications that are going to be or are already being used in the EEG space. And this ranges from easy to fairly hard from the standpoint of generating AI that can contribute to this process. In terms of the specific needs for an EEG-based AI system, the data inputs are going to be really important. Generally, in a lot of our data sets, the quality of the EEG is not very good over the long term. You guys know this better than anybody, that electrodes can fall off, there's artifact, there's noise, so on and so forth. And that stuff is going to contaminate our ability to really generate effective AIs without a lot of curation. Annotation of that data is very, very rarely performed, and it's not contained in the data set. And so the ability to do supervised learning on those data sets is very challenging and requires a lot of preparation of the data before it goes into the engine. And ultimately, it's very, very rarely that you see EEG data integrated with systemic physiological data. On the machine learning side, I'm kind of glossing over that because I think there's going to be a lot of different tools that we can use over time. But on the output side, I think it's really important that we identify some of the targets that we're looking for. A lot of the focus is on seizure detection, and we could talk about that for hours, but ultimately, even if you can diagnose a seizure using an AI, how do you provide treatment recommendations? There's a huge gap between the diagnosis or whatever you might see in the EEG read and ultimately what the clinical action is going to be. And there's always going to have to be, for some period of time at least, somebody in the middle that can provide that guidance as far as what to do about the information that comes out of the system. And then ultimately, who's going to be responsible for turning that information into an action? I personally think that EEG technologists, the kind of the specialists in the space are going to be critically important for quite some time for translating the information that comes out into something that can be done on a clinical basis. And so on a theoretical level, I think there's going to be some easy, some harder, some moonshot type stuff in the EEG space. As an example for some of the easier stuff, sedation monitoring is the most obvious one. So, in this case, you can see there's a patient that was receiving sedation and was in burst suppression. And then as a result of looking at the waveforms and then also some process data looking at burst suppression ratio, you can say, yes, the patient is in burst suppression. We don't want the patient in burst suppression. So the system can say, turn the sedation down. So in this case, the sedation was turned down. You can see there's a response in terms of return of continuous EEG. Suppression ratio goes down. This is the simplest, easiest kind of version where it's very, very simple analysis and it can be very quickly translated to clinical practice. The harder stuff is probably going to be things like stroke detection, state change, things based on symmetry or power analysis. This is going to probably rely more on processed or quantitative EEG derivatives rather than simple waveform analysis. There's increased dimensionality there, right? We can look at alpha frequency, beta, delta, gamma, so on and so forth. Time, time windows, all of those things can make a difference. And as an example, you can see this is a patient that has a very subtle asymmetry. This was a patient with a subarachnoid hemorrhage who had left-sided cerebral vasospasm. And, a trained EEGer, if you will probably pick up on this, but this is something where really identifying the extent of change, what's relevant, so on and so forth, you can see that there's asymmetry here, but how much asymmetry is important. However, the simple fact that you develop an asymmetry in a particular clinical setting can drive clinical intervention or drive clinical action, whether it's imaging, endovascular therapy in this case, And ultimately, it's the bedside providers who are going to be using that information to move on to the next step. Personally, I think the hardest stuff in the EEG space is going to be seizure detection, brain blood flow optimization, so on and so forth. And part of the importance of that is that the clinical setting is critical. If you have a patient with known epilepsy and you're doing an EEG and you see epileptiform activity, that's a very specific case. However, if you've had a patient that had a severe traumatic brain injury and you're seeing epileptiform activity, or somebody who has elevated intracranial pressure, or somebody who has low blood flow in the setting of receiving ECMO therapy, that's a lot more complicated. The other thing is, what is a seizure, right? So this is obvious seizure activity in a patient with a cardiac arrest. You can see it very easily with the processed EEG data. And in this case, the clinical intervention is probably fairly straightforward, maybe even accessible to the intensivist taking care of this patient. But in other cases, it's going to be a lot more subtle. We're talking about things on the ictal, interictal, kind of continuum, if you will, where there's a lot of different labels: Serpids, birds, Lerta, Gerta, so on and so forth. And the question is, with those various labels that can be applied to that data, what do we do about it clinically? This is an example of a patient with autoimmune encephalitis. And in this case, anti-seizure meds may be one treatment, but treatment of that autoimmune problem with immunosuppression is probably a better way of treating these over the long term. And so that's where it gets a lot more complicated in terms of the output. And then the moonshot stuff, there are people starting to work on this, and this is where it will go, but we don't even really have the data yet on a clinical basis, and the actions are totally experimental. This runs anywhere from things like Parkinson's or Alzheimer's diagnostics, and then ultimately following those patients and ultimately optimizing the therapy. People are talking about using EEG for diagnosing schizophrenia or depression. Moving into the outpatient scenario, if you have a family practice physician who's providing somebody with an antihypertensive medication that we know might have effects over the long term on their brain, EEG could potentially be used to optimize their blood pressure medications to maintain cerebral blood flow. People are starting to look at EEG as a biomarker for drug trials. Ultimately, neuromodulation, we're talking about deep brain stimulation, the NeuroPace device, so on and so forth. And then ultimately, way off in the future, brain-machine interface. So I think this is almost an unanswerable question, but how fast will we start to see AI in the EEG space? I think going back to that level of complexity, the simpler stuff, I think there's already some really simple versions of AI that are already being used there. BIS, SedLine, these are things that are more driven by really simple algorithms, but that concept is there where we've got very, very targeted clinical applications. We have a good data set and we can get those to the regulatory process and deploy them fairly easily. However, we have to start talking about hospital approvals, payers, so on and so forth. Getting into things like seizure diagnostics and kind of more advanced applications of the data that's coming through, it's at least years off. And I think there's going to be a lot of other applications of AI that are going to be kind of mind-blowing before we get to that point. So where do people fit in, and ultimately where do we fit in the whole EEG AI space? I think there's a big question about human replacement versus human augmentation. So if you are a family practice doctor or an ER doctor or a fourth-year medical student, you probably all saw that ChatGPT got a 90% or higher on all three steps of the medical licensing exam. That's a little astonishing. It kind of tells you the kinds of things that it can do so long as the information is available to it and it can answer the questions in a way that the data supports. Ultimately, I think human augmentation is where a lot of this is going to go, and particularly for improving workflows on our side. I think a big challenge is going to be, how do we confirm that AI is reliable? We're going to see a lot of this in the self-driving car space, but it's going to be even more complicated in the medical space. People are going to want to know, can we sue the computer? Who's responsible? Ultimately, those are challenges that have to be addressed. Whether or not AI can answer all the questions. So as a physician walking into a patient's room, I have to be prepared to answer any questions that come at us. Same thing with you guys in terms of interpreting EEG. It's easy for us to say, well, we have some thoughts. It could be this, it could be that, but ultimately you come up with a conclusion or there is no known answer. that may be a little bit trickier for AI, and we may not even know the kinds of questions that we're asking it to answer. I think a really critical point is that ongoing human input is going to be absolutely essential for ongoing optimization of these systems and ultimately for future product development. The people who work in the EEG space are the ones personally that I think should be developing future products, because you see the needs, you see the challenges, you see the practical realities, you see the opportunities, but you also see the variables that are associated with really developing a meaningful AI that will functionally change the way that we practice in this space. So in terms of the critical role for EEG technologists, I think you're going to be absolutely critical for early adoption and application. You guys know the whole EEG world front to back, and I think understanding where this fits in intelligent ways is going to be a real opportunity. I would not see it as something that is a threat. I think it's something that is going to functionally and fundamentally optimize the way that you practice. And I think dissemination of that kind of supportive technology to people who are unfamiliar with these technologies, there's going to be this critical role for people who are familiar with the EEG space. Ultimately, clearly, we're talking about a lot of bridging time between now and the AI that solves the whole problem. And I use the phrase neurotelemetry because that's ultimately what I, as a neurosurgeon, and what we're interested in is really fundamentally changing the way that we can use EEG to take care of patients and take care of the brain in a lot of different clinical settings. And I think there's going to have to be a huge role on the brain side for EEG technologists and other EEG experts to provide this kind of information that can be augmented with technology. Ultimately, as I mentioned before, we need better annotation of this data. What is a seizure? What is an asymmetry episode? So on and so forth, so that we have better data sets to feed into these machine learning algorithms over time. And then ultimately, as I mentioned before, what are we going to develop? What is the product that we're trying to create that solves this particular clinical application where there's a required action? And I think the idea of just generating more diagnostic terms through data analysis, right now, if you read the ACNS guidelines for EEG interpretation in the ICU, 15 to 20 pages of wiggly lines that all have different labels. But I, as a neurosurgeon, have no idea what to do with that information or how to leverage that information. And I think as we move into the future, knowing what we need to be answering and developing products that are based on that knowledge is going to be really critically important. So thanks very much. And obviously, we'd love to take some questions and looking forward to hearing from everyone.
So if you have questions, go ahead and enter them into the chat area. Just go ahead and type them in. If you don't see the chat area, down at the bottom right-hand corner of your screen, there is the little hamburger sign, and that allows you to just type that right in. So we'll give a few minutes here just to see if there's any questions that pop up. Thank you for this particularly challenging presentation. Clearly, we're at the early stages of the development of AI as it applies to neurodiagnostics. But at the same time, I think it's one of those areas that will lead to better patient care eventually, because right now we're still struck with the lack of information as to what's going on with the brain with many patients. And part of that is, the fact that not every patient is being monitored that should be monitored. And therefore, any technologies that increase the ability of us to watch the brain and to see what happens in conjunction with other physiologic changes definitely will add to the ability to care for patients and to treat them quicker and probably more effectively. So I'm still waiting to see if there's any questions that pop up. And again, you can enter them into the chat area. We'll give it another minute. And if nothing pops up, then we'll end the session. So there's a question here that says, it sounds like there's a possible job that really could be defined for EEG technologists in the future that relate to populating AI data or data into an AI system specifically. Do you have a comment on that?
Yeah, I think I think there's going to be a multiplicative series of roles for EEG technologists in this space. As Jeff, as you mentioned, there is a massive underutilization of EEG right now, and ultimately, part of that is related to a shortage of technicians. Part of it's related to the kind of limited functions of the technology that exists. But I think that all of these things, what can be captured are all these different, verticals under the kind of the same, role, if you will. And yes, I think people who are used to looking at EEG and able to identify patterns in EEG that have clinical relevance are going to be extremely, extremely valuable going forward.
Another question really is, can ChatGPT in particular aid in the education and training of EEG techs?
Yeah, so I think we're just scratching the surface of ChatGPT. Conceptually, it has access to basically anything that's searchable, on the web, and it can do that extraordinarily rapidly in a way that's extremely advanced beyond what humans can do, in a very short time frame. And that's kind of one of the reasons why I brought up this, query that one of my colleagues put in there, is that on a conceptual level, we would be able to write down all of those steps. If somebody posed that question to me, I could probably work through that. Some of that's explicit knowledge, some of it's implicit, but very, very rapidly, that's what it came up with. That is probably not published anywhere. There's probably nothing that if you put that search into Google, I don't think that would just pop up as been previously recorded by somebody. Where I'm going with that is that I think that ChatGPT is going to be, and things like it are going to be transformative in terms of very rapidly putting together, meta-analyses and consolidated information much, much faster than humans will be able to. So I think on the education.
So another question here. Any thoughts on how this technology will work alongside the surgeon in driven interoperative neuromonitoring situations? And if you're looking at, AlphaTech or any of the other, systems that are out there.
Yeah, so I may kind of reframe that a little bit in terms of, the existing workflow and ultimately where things could go. So the existing workflow, whether it's IO&M or whether it's EEG, so on and so forth, is very kind of human heavy, if you will, right? So there's the component of it that's necessary for analyzing the data collection, whether it's sticking on the electrodes, putting in the needles, setting up the machine, setting up the montage, so on and so forth. I think we can solve a lot of those problems with technology, where you can maybe move people away from the physical labor part of it and more towards the brain part of it. And then over time, as the AI potentially becomes better and better, there are going to be things where it would help a surgeon. So for example, if I'm doing a carotid endarterectomy and I'm using EEG to determine whether I need to place a shunt when I cross clamp the carotid, that's something that's probably fairly simple, straightforward. An anesthesiologist or the AI could tell me that, hey, you put the clamp on, we wait 30, 40 seconds. Yes, we're losing alpha power on the affected side, so take the clamp off, so on and so forth. I think relatively simple things like that are going to be, the next step. Once we start looking at SSEPs, motors, I think there's going to be ways where the system can report back that there are reductions, whether or not that's important, whether that's surgically relevant. I think there's always going to have to be that layer, at least for the short term, where you have somebody that can say, well, the patient's core temperature is low, and so we may be losing responses, or the anesthetic is high, or there's still paralytic there, and so on and so forth. So when you start to think about all that complicated data that needs to flow in, all of that information doesn't have to be accessed at the bedside. That could be more virtual, but it's going to be some period of time before those more complicated things can be done and completely remove the role of somebody who knows what they're doing in that setting.
Very good. Well, let's wrap it up there. Appreciate your participation, and thank you for all that attended. As I stated, we'll be sending out an email to you so that you can complete the evaluation form. And thank you very much.
Thanks very much. Appreciate it.
Good day.